A tough assignment, but I'm really excited that we're doing it. I didn't do this last year with my students, and I'm really excited that we get to do this. It's a little bit tougher chemistry, but I feel like that together we can tackle this. Okay, so number one is asking us to be able to look and see, okay, AgNO3 breaks down into its ions, and potassium iodate then breaks down into its ions as well. And then you can see that we have silver iodate, I believe is the name of that term there. So we have AgIO3, okay? And they want you to be able to consider the solubility of this and if a precipitate forms. So we have to compare um, the Q value, which is calculated for this, when we have to find that using concentrations, we need to compare it to the K value that's listed here. And that's definitely hinted at right here in the answer. And so how do we do that? And let me just take you on that journey. Let's do it right here together. Okay, so I'm gonna just kind of get wild. I'm gonna take up a lot of space here. So we're gonna go with AG. Let me see if I can change colors. Let's go with some a little bit darker. Okay, so we're going to go with AgNO3. Okay, and team, I'm not going to use subscripts. It's going to be a little bit messy, but we're going to do it. Becomes Ag plus, okay, plus NO3, and 3 is only a minus charge on it. Okay, so that is Ag. Then we have KiO3, okay, and that breaks down into, when we put it into water, breaks down into K ion or potassium ion plus iodate ion, which is IO3, and then I believe, yeah, that just has a 1 minus charge on it. Okay, and so then they want us to do is they want us to use that information to say, okay, we've got an Ag, a silver iodate, and I want to look up and see what that chemical is to make sure I'm not saying that wrong. That'd be very embarrassing right now. AgIO3, and see, well, what's it going to break down into? And you guys already have guessed that. It's going to be Ag positive, okay, plus IO3, and that's just a negative value because there's only one of each, one of each, one of each. Oh man, that kind of makes our life a little bit easier, and I'm kind of grateful for that because we don't have to worry about exponents, etc. We can just worry about that. Okay, so if we can just worry about this here, well, that's great and all, but how do we calculate, okay, and we can see where we're getting that. We get this Ag from the first one, we get the IO3's concentration from the second one. How can we do that calculation? So let's do that really quick. Let's see. I'm going to do that calculation right over here. Okay, so there we go. Okay, we've got this calculation. Oh hell, let me just put it right over here. What do we got? Do we got a more exciting color here? I don't know, I guess we'll use red. That'll pop a little bit better. Okay, so we've got AgNO3. I have 0.5 times 4.0 times 10 to the exponent negative 3. Okay, and that is liters on this one, okay, times moles per liter, and this is actually in moles per liter, so the liters cancel on that one. But all of that is going to be divided by, okay, is divided by, I'm going to put on this next line over here, is divided by, oh shucks, I think I was Was I able to make a line here before? Yeah, I was. Well, good Lord. Well, let's make a line. Thanks for your patience, team. One of those moments, man, where we got a little more time to do this on the board. Whew, it'd save us a lot of time. But there we go. Okay, so now we can type it in. And so we calculate, this is to calculate, we go liters times the molarity leaves us with moles. And then if we divide that by the total amount of liquid, and that's going to be that's 50 milliliters, okay, plus 50 milliliters, okay. And if we do combine that, get 100 milliliters on the bottom, but I'm just going to leave it in this form so that you can see that. So we run this through our calculator. Let's say that we do that. Okay. Let me put a little space there so that you guys can see that right there. There we go. So we start with 0.5 liters. Ooh, did I mess that up? Yep, I did. I did. Good Lord. Okay. 0.05 liters is what we start with of our sample, and then we multiply by our molarity, and then that gives us moles, and then we divide by the total amount of liters, and this, all of this right here is going to give us our Ag concentration, okay, which, oh boy, I used the wrong bracket, our Ag concentration, which is, in this case, 0.002 molarity. Perfect, okay? And let's see if I can then do the same thing. Let me see if I can do the next one in, well, hell, let's see what we got. Purple. Let's go with purple. Let's see how that one flies for us. Oh, I can handle that. That's a color on the screen that's not hurting my eyes right now. I don't know. Let's see. Okay, let's go with like this green. It's a little bit easier on the eyes. Okay. 0.5 liters. Okay. And then we're going to multiply by, and then for this one, we have 1.0 times 10 to the exponent -8. Good. Oh, that's a really small number. Okay, and this is moles per liter because it is molarity, and we can see that one right there. Now all that together, let's change this color and put a little green line under it right here. There we go. Put a green line under it. Nice. And we got 0.05, which is that 50 milliliters, plus 0.05, another 50 milliliters. Type all that in, and then we're going to be left with our concentration of iodate ion, 3 minus, there's our ion right there, is equal to 0.0005. Okay, and it makes sense. It's significantly smaller because it's a lot less there. So, and I guess I should put another set of brackets around this to make it clear that we got to do everything on the top and then divide that by everything on the bottom. There we go. Beauty. Nice. We can live with that. Okay, so I've got my two concentrations there. And now that I have those two concentrations for right at the very beginning of the reaction. Now KSP is at equilibrium. Everything's settled. It's already gone down to this nice equal value, and that's 3.2 times 10 to the -8. That's what the the constant is for the equilibrium, or the solubility constant right there. But for when we first mix these chemicals together, that's the Q value. And so let's type that in, and let me see, heck, let's see what blue looks like on here. So we've got QSP is equal to my concentration of Ag plus ion times, okay, the concentration of the iodate ion. Okay, and the nice thing is there's no coefficients, so we don't have to worry about like some of the work that we would have to do by putting exponents here, like to the power of 2, etc., because we don't have any. They were nice to us on this problem. So we've got QSP is equal to 0.002 Well, my mouse is getting away from me here. Alrighty, 0.0005. Man, that's a lot of zeros. Molar. Okay, we multiply these together, and my QSP value comes out to, oh well, a little nervous. Okay, because it was several hours ago when I did these calculations initially. I just want to double check. So the calculator I use when I am working is Desmos. There it is. Okay, and I'm going to paste this one in there. I'm going to get rid of my molarities, multiply those together, and I've got 1.0 times 10 to the negative 6th. That is what my work is showing me. Okay, so I've got 1.0 times 10 to the negative 6th to the exponent negative 6. Got it. And that is my Q value. Actually, well, as far as the units, it doesn't really matter. Now I just need to compare and be like, okay, is Q greater than K? Is it less than K? So I've got something times 10 to the negative 6th or times 10 to the negative 8th. Which one of these numbers is bigger? The Q is going to be bigger. Okay, so it's going to be QSP is actually greater in this case than the KSP is. Okay, I don't know what color we can assign this. The final countdown. QSP is greater than KSP. So, does a precipitate of AgI03 form? And I can see that equation right here. Let me see if I can change that. Okay, let's highlight that. Will it let me highlight? No, it won't let me highlight. Okay. Yeah, it's all or nothing. But I just showed you guys right there. That is the equation. And it's actually an equilibrium, so it's going to go back and forth. Let's go here. So it's going to go both directions with that one. And if it goes both directions, the question is Q or K greater? Q is greater, okay? So that means that there is going to be more precipitate that forms. And we saw that in our notes. We just learned that, okay? And if you need a refresher, I'd go back and check out that one. So I'll draw my line here and say the answer is B, okay? That was a lot of work to be able to figure out B. I was really excited that the other problems were not as hard as this. This one was the tough one in my opinion. Number 2, here we go. A beaker contains a saturated solution of magnesium hydroxide in distilled water, as represented by the equation above. If the pH of the solution is decreased, so let me really quick just remind myself what decreasing the pH of a solution. So that means the pH value goes down, which means it's going to become more and more acidic. More acidic acidic or more H plus. There's going to be more H plus. So if there's going to be more H plus, okay, which of the following is most likely to occur? So let's look at this. If I add more hydrogen, okay, more hydrogen is going to make water and reduce, and so it's going to steal the OH ions. It's going to steal those OH ions and reduce those OH ions. So there's going to become less products. So more of the MgOH is going to need to dissolve to make some to replace them. Okay, so this is going to cause the KSP to increase, or will it decrease, or is the concentration going to increase or decrease? Now, here's the thing. Because this is the equilibrium value won't change. But the Q value, because we've made a specific change to then go back to equilibrium, the Q value is going to change. And that, so that's why we can eliminate right off the bat. We can say, no. K isn't going to change here. We're not worried about K changing. So now it's got to be either the concentration of magnesium ions, okay, as a product, okay. Once we remove the OH, are we going to make more products? Is the reaction going to shift to the right and make more products? Or is it going to shift back to the left and make more reactants? So what we're looking for is this magnesium ion. Is it going to increase or decrease? And we know from Le Chatelier's principle that removing products will cause it to shift to the right, and it will also make more of the products as well. All of the products will be created in more abundance. So therefore, we know that the answer is C. Okay? All right. And that has to do with Le Chatelier's principle and that shift. Okay, so let's go and take a look at the solubility equilibria. Now, here's the first question they're going to kind of trip people up with. They're going to say, hey, let's compare these. And sometimes you'll start with something that's like FeCO2, which is 2 molecules, and then it will go to and split, sorry, that's my bad, Fe iron, CO2, that's carbonate. Wow, that shouldn't take me that long. Iron carbonate is 1 molecule, and then it's going to break down into iron and carbonate, so it's going to be into 2 molecules or 2 ions. And then what's wild and what's actually kind of convenient for us is these are going to then break down and do the same thing over and over. We have 1 nickel carbonate, 1 molecule breaks down into 2 molecules. And I should remove that S because that's annoying me. Doesn't really matter, but just to be extra clear, it's 1 molecule, 1 molecule, 1 molecule breaking down into 2 molecules. Because it's 1 that breaks down into 2, we can just compare their KSPs and then answer the question. Based on the information, if any of them were to be from 1 into 3, or 1 into 4, or 1 into other molecules, we would be screwed and we couldn't do that nice and easy comparison. But here they gave it, this is an easy question. Really nice and simple. Lets us be able to just compare their KSP values. Based on the information in the table above, which of the following arranges the compound in order of increasing molar solubility? Okay, so we got to go increasing is going to be smallest molar solubility, or smallest KSP to largest, okay? So the smallest one is going to be PbCO3. We want that to be the first thing listed from smallest to largest. Okay, so the smallest one is number 1, PbCO3. And I think that we just eliminated all of the other possibilities because it needs to go from smallest to largest. Number 2, the next bigger one is FeCO3. Okay, which is here we got 2, and I'm being extra rating all of these, but sometimes you need to when you're going through and doing process of elimination stuff. And then the final one, which is the largest KSP, because, yeah, that number is significantly larger than the other one. This one has 14 zeros in front of it. This one, or 13 zeros in front of it. This has 10 zeros in front of it. This has 6 zeros in front of it. So yeah, for a decimal, it's way bigger. All right, I just did it, and I think that we've narrowed it down, team. I think it's pretty easy to see which one our answer is here, and that the answer is C. Okay, and I'll actually circle this one here so that you can see that. It is C, and we did it. Now let's look at number 4. And 4, ooh, there's a little bit of trickiness here, but if you watched the last video and you took notes, there's a little cheat that helps us out big time on this one. But if you didn't, it's really easy to get lost on this one. And I remember last year when I first approached these problems, I was kind of mad because I was like, hey, what the heck is happening? But now that I better understand molar solubility and what it's actually doing, it's actually a lot better. So because I can't really type it out in any way that's fancy, you guys might have already picked up on the fact that this is my symbol for equilibrium, those two arrows going back and forth in both directions. So we've got Ba2 plus is that ion plus, and then we actually have a coefficient on that one, F minus. Okay, so we got two F minus ions there. Okay, and let's see what we got here. We got an ice value. Got an ice. All right. So for the solid, we don't need to really do any calculations with something that is a solid because, yeah, team, it is a solid. These are aqueous ions, so we're not going to have to worry about them. And again, it's just using that rule that if we put a solid into water, and they gave that to us, that then it's going to break down into those two other things. Okay, and so let's see here. And they also added something before we can just jump right in and finish our ice table. Yeah, it's right here. Let me see if I can actually just take some time to go and look at this. So team, if we take this value right here, and we were to put this in the same beaker, the sodium, okay, and the fluorine would split, and they would go and become sodium ions and then fluorine ions separately. They would actually become separate, and those fluorine ions would then contribute to the other reaction taking place, the other equilibrium, because they're ions. They would be added as wherever that's at in the equilibrium, which in this case is in the products. Okay, and so I'm going to indicate that as I fill out my ice table here. Okay, let's push the wrong button on that. Sorry, team. A little bit of whiplash there. Wow, let's go here for our ice table. For the initial on the barium, we start with 0. Okay, and if we go over to our fluorine, we start with point. We also have 0, but we also have the 0.25, 0.25 from the sodium fluoride. Okay, the sodium fluoride allows us to be able to put a little bit extra at the start. Okay, and that's important. And we're going to come back to that. So then what happens when the change happens is we add an x, and how here, because there's a coefficient, we've got to add a 2x. Okay. And then once we get down to the equilibrium, it's going to be x. Okay, and if we go over, technically it should be 2x plus 0.25. Now, because our molar solubility is so small, this KSP value, and remember that K, when we've learned about it, is products over reactants. But for this one, we can't calculate a reactant because it's a solid. It only works for things that are non-solid, so it's just K in this case is just products. And remember that if K is equal to 1, then there's equal exchange both directions. If it's greater than 1, it's going to make more products. And if it's way less than 1, it's only going to stay as reactants. And so with this tiny little K value, little teeny K value, we can assume, okay, that we are not going to make very much product. And if we're not going to make very much product, we can take a shortcut. And that means that we can actually get rid. I better. I don't know what I'm moving around there. Sorry about that. Here we go. If we're going to move things around, okay, let's, oh man, come on. Give this back to me. There we go. Okay. We're going to cross out that 2x in our calculations. Okay. And so now we can calculate our KSP and we can solve for x. So if we solve for this x value, okay, that's what we're trying to solve for, this x value, that is our molar solubility right here. Okay, and so let's do that. Let's do that really quick. So KSP is equal to the concentration of the reactants, which is Ba2 plus, okay, times F minus, but we need to make sure that that is raised to the power of 2 because it has a 2 coefficient. Okay, so then let's just do that. KSP is equal to X for BA is my equilibrium value, and then for the other one, it's 0.25 for its value. Okay, so if I've got X times 0.25 raised to the power of 2, what about this? This KSP is actually given to me above as 1.8 times 10 to the negative 7th power. Okay, and so now if I solve for x, my x value, okay, and like I said, this is way easier on a whiteboard to be able to kind of follow this and track it. And if you need me to do it for you again on the whiteboard, I can. But with some simple algebra, I can get x is equal to 2.9, okay, times 10 to the exponent. Let me bring that one closer. Negative 6th, and that is in molar because molar solubility is molar. Okay, moles per liter. That is my value right there. Okay, and I'm going to change this to a nice green color, and that's it. 2.9 times 10 to the negative 6 molar. That's it. That's my molar solubility, and so you can type that in just like that. Make sure that because we've started with 2 sig figs up here, 2 sig figs, that your answer is in 2 sig figs right here. So if I were to type that in, that would be 2.9 times 10 to the exponent negative 6. And there it is. That's it, team. We did it. That was a 30-minute explanation for 4 problems. You know that it's tough. Win.